Hello folks, and welcome to this lesson on Gibbs energy and equilibrium constants. By the end of this lesson, you should be able to explain the relationship between Gibbs energy and equilibrium constants and perform calculations related to Gibbs energy, equilibrium constants, and reaction quotients. First off, let's talk about the relationship between Gibbs energy and equilibrium constants. The two ideas are very much different facets of the same idea of, is this reaction going to go? When will it stop? These sorts of ideas. Now, of the two, the Gibbs energy portion is around the idea of, if we're looking at spontaneity, will this reaction happen if you leave it on its own? Gibbs energy is about that. Is it spontaneous in this particular direction? And then we have equilibrium constants, which tells you when a reaction is going to stop. Of course, I've put the word stop in quotation marks because of the fact that a reaction never truly actually stops. It just appears to stop because that's the point at which the forward reaction and the reverse reaction are at the same rate. So it doesn't look like anything's happening. It has reached dynamic equilibrium. So if you have a negative Gibbs energy, that means that as the reaction is written, it is going to be spontaneous in that particular direction. And then you're going to have an equilibrium constant, and so again, if we have that Gibbs energy that is negative, it's going to go in this direction and it will stop once it hits equilibrium. And that equilibrium, you know when it hits equilibrium based on the equilibrium constants. So let's look at this in a sort of qualitative view. So if we're going to look at a particular reaction where the delta G is negative, you know that it's going to happen spontaneously. You know that this reaction favors the products. So that means that your K value is going to be big if you have a reaction that happens spontaneously. Now, if you have a reaction that is already at equilibrium, for that particular reaction, the overall, the K value for that overall reaction is going to be around 1. It doesn't particularly favor the concentrations of those reactants or products. All of those concentrations are going to be pretty much the same if you have a reaction that has a delta G value of 0. And then, of course, if you have a reaction where the delta G is positive, that means it's not spontaneous in that direction. It means that the reaction definitely favors the reactants over the products. So that means that point, that ratio of products and reactants, that it will be at equilibrium is going to be very, very much towards that side. It's going to be a smaller number. Now, of course, we are a science course, and so we are going to use some graphs to represent this whole situation. So this is a framework that we're going to use. On our x-axis is the composition of the reaction mixture. So basically what we're going to do is we're going to take this particular reaction, and then we're going to say at the leftmost side, it's all reactants. So the concentrations are 0 for your products and the full for your reactants. And then at the other end, we are going to have only products, no reactants at all. So this particular graph is closed off because we actually are not going to see what the relationship is as everything continues. We have a definite stop when we have all products. For our y-axis, we're going to be looking at Gibbs energy. Note that it's not delta G that we're looking at here. We are looking at the absolute value for Gibbs energy. Now, how does that make sense when we can't actually figure out what the absolute values of Gibbs energy, particular reactants or products have? We can only actually measure changes in Gibbs energy. Well, it's sort of like those other potential energy diagrams that we did before. You remember the ones where you have like your reactants here, your products are down here. We still have an axis of potential energy, but we never label anything because we don't know exactly what those values are, but we can still use it to represent what that delta H is, what that change is. So we're doing the same thing here. what the value is going to be the absolute Gibbs energy, though we're not actually going to be adding any numbers to this axis. So let's look at a situation where we have a negative delta G, so this reaction would happen spontaneously. If we are looking at a negative delta G, that means our reactants have more Gibbs energy than our products. So over the progress of the entire reaction, you are going to have a decrease in your Gibbs energy. So for the sake of just showing a particular reaction, let's say that this is the amount of Gibbs energy that our reactants and the system with only reactants in it has, and this is the amount of Gibbs energy that the system with only products has. And so the delta G is going to be this difference. This is a delta G of the reaction. Now we know that if we have a negative delta G, it is spontaneous in that forward direction, which means that this system will reach equilibrium somewhere along here. So if we say that this is sort of our halfway point where the concentrations of your products and reactants are going to be pretty much even with each other, we are going to be looking at, for this particular system, a K value that's going to be somewhere over here. For the sake of just this drawing, let's say that you reach equilibrium when the ratio between your products and reactants are over here. Now, remember that low Gibbs energy is what is most energetically favorable. So based on that, when your system is at equilibrium, that is going to be when the system is at its lowest amount of Gibbs energy. So that means that when we are at our equilibrium concentrations, your Gibbs energy for this system is going to be at its lowest. So based on that, if we say that we're going to start with all our reactants, as the reaction continues to progress, it is going to keep on, the Gibbs energy of that system is going to keep on decreasing until you reach those equilibrium concentrations. At that point, the Gibbs energy is going to be at its lowest. And that means, at this point, that's when the Gibbs energy is lowest. That's where your reaction is going to stop. It means that if you want to actually push it all the way so that you do form all products, that Gibbs energy is going to increase. Now, a part of you might think this doesn't make sense. If you have a negative delta G, that means it's spontaneous. Shouldn't everything go all the way to the end, and so on and so forth? And the thing is that if you have a reaction that really does go to the end, that means its K value is super, super, super huge. And so for that particular reaction, the graph is probably going to look a little bit more like this. Now, you can see my line is very wobbly, but you can see that if you push that equilibrium concentration even further, then it can get to a point where everything is much closer. The increase from your Gibbs energy at equilibrium to your products is not going to be all that different. So this, where you have a huge, huge, huge Kc, is going to be a situation where the reaction tends to go to completion. Now, you're not always going to start with all reactants or all products. You might actually start somewhere in between. So if you have a mix of your reactants and products, you can still use this graph to figure out which direction your system is going to go. In the same way that you can calculate your reaction quotient, your Q values, to figure out which direction it's going to go, you can use the same sort of thing here. So say that you are at this point, this is your ratio of your reactants to products. From here, you can see that the Gibbs energy will decrease if you go further right. So you know that it will be spontaneous in that direction, but it will not be spontaneous in the other direction. And you also know that if you have your ratio and it's somewhere here instead, then you know that the direction of the system is going to go in the direction where the Gibbs energy is going to decrease, so the reaction will spontaneously go in that direction if this is your ratio of your reactants and products. So in a similar way, you will be able to draw graphs for other types of reactions as well. So if you have an overall reaction that has a delta G of 0, so when your delta G is 0, that means your Gibbs energy when you have all reactants or all products is going to be the same. Now, there is going to be still an equilibrium concentration, and that is going to happen. Equilibrium is going to happen when the ratio between your products and reactants are pretty much the same. So that lowest part of your graph is going to happen somewhere smack in the middle. And then if you draw the rest of the curve, it's going to look somewhere along the lines of this. Whether it's higher up doesn't really matter as much, but at any rate. And then in the situation where your delta G is positive, you know that your products are going to have more Gibbs energy than your reactants, and equilibrium is going to happen in a concentration ratio that very much favors your reactants. Now with these two graphs, you can still do the same thing where, oh, I know that my ratio of my reactants and products are right here. Which direction is the reaction going to happen spontaneously? Oh, it's going to go to the left. Now, we are still a science class, so that means if we can quantify all our stuff, we are going to quantify it. So, quantitatively, the relationship between delta G and K is this particular reaction. Now, this R is that same gas constant. It's your 8.314 joules per mole per Kelvin, and usually with your delta G values, you're going to have kilojoules per mole, so make sure you do those unit conversions when you're using this particular calculation. Now, you know that with our graphs, you can sort of take a look at that shape. You can see where your ratios are and then determine which direction is it going to be spontaneous. You can do that sort of a calculation when you don't have equilibrium concentrations either. So if you know that the overall reaction has this particular delta G, you can find what the delta G would be at a certain reaction quotient, so in certain usually not equilibrium concentrations are, and then based on the sign of this, you will be able to determine if it is going to spontaneously continue in the forward direction, if it's already at equilibrium, or if it's going to spontaneously move in the other direction, in the reverse reaction. Now, with this particular lesson, realistically, what are the things that you are going to be asked for? Why do you need to know this stuff? Well, the relationship between delta G and K, conceptually, you should be able to make sense of the fact that they are very much related to each other. And you should be able to predict what signs and value sizes are going to be in a more qualitative way fairly easily. Or when you're given certain values, you should be able to predict what happens. On a really rare case, they might make you sketch out one of those graphs and label it, or they'll give you one of those graphs and tell you to use it when they give you specific conditions. Though I don't honestly see that necessarily happening. It is a possibility. And then you have these equations as well. Now, why use these equations when you can just find out the reaction quotient, compare it with K, and then figure out which direction your system is going to move in? Well, this becomes a little bit more helpful if you have to do something, say, lab-related, and you need literature values that you can calculate, or theoretical values that you can calculate, and using delta G is the most helpful, or you need delta G is sort of the way that you can get to your other values. That's where this particular thing can be helpful. And of course, in a test situation, you can get a problem like this, where it's going to make you use the equations themselves. So, pause the video, take a look at the question. Now I'm going to go through these rather quickly because of the fact that It's find the right equation and then make sure you plug everything in. It's nothing particularly groundbreaking. So for the first question, it wants you to find delta G naught. So you have to go back to that lesson, and then you're going to use that particular equation. You're going to get negative 32 kilojoules per mole, and it's going to end up being spontaneous. For the second question, it is telling you to find the K value. You have found delta G from before, and so you toss it into the equation. You're going to find that K is 3.5 times 10 to the 5, which means that the forward reaction is quite favorable. That is a very large K value. This should not be surprising, the fact that the forward reaction is favorable, because we just found out that the forward reaction happens spontaneously. So yeah, again, if the forward reaction is going to happen spontaneously, it is going to favor that forward reaction. So for that third one, they want you to find out what the delta G would be for that system at this particular Q value. So with these particular concentrations for your reactants and products, what is going to be the delta G? So you toss in your numbers, you are going to get a delta G of 2.4 kilojoules per mole. So this is a positive number, and therefore at this particular Q, with this particular combination of concentrations of your reactants and products, this reaction is going to be non-spontaneous in the forward reaction, of course, in the forward direction, of course. Now, of course, you can check your answer for this particular third question by taking a look at the Q and the K value. You know that this is your K value. You take a look at your Q value. You see that this is bigger than that. So that means you have more products than your system would have at equilibrium. So that means it's gone past those equilibrium concentrations. It is going to favor the reverse reaction. So there you go. That's the end of this lesson. I'll see you next time.